Hey guys, it's Miss Miklos, and today we're going to talk about actually graphing all the polar equations. So it's going to be a really fun day. And I'm not being sarcastic, it is fun. So we're going to learn how to do each of these particular types of graphs, and that's going to be this first video. Then I'm actually going to go through a second video with you guys that's going to have all of the graphs mixed together. Just to kind of show what I would expect you guys to be able to do in terms of figuring out like what the graph is and all of that. Just like when we worked with conic sections, sometimes it's really easy to graph when we know, okay, this is a rose or this is a circle, and it gets a little bit tougher once we kind of throw everything together. So that is the format. Yes, it's going to be a longer video, but we're learning a ton of information. So with that, here we go. Our first type of our first type of polar graph is what we call a rose. And we saw a little bit of a preview of this last lecture when we graphed by hand and we did all the ordered pairs and it looked really nice and pretty. And we have two different general equations for roses. Okay, so this would be something you guys should have memorized. We have r equals a sine n theta and r equals a cosine n theta. So some things that I want to point out about this. First of all, these are both monomials, so we don't have addition or anything like that going on. A and n both represent constant values, so we're going to see numbers there. So some information. The first information that I want to kind of cover is how do we find the first petal? And we kind of saw that a rose looks like a flower. It has all these petals, and we can spend all the time we want figuring out ordered pairs, but it's going to be much quicker if we have some shortcuts. So if we have a sine equation, our very first petal is going to be at 90 degrees divided by n, and at 0 degrees, there we go, doesn't want to finish, if it's at cosine. And I just want to note that when the equation is negative, the first petal is reflected 180 degrees. Okay, so we've already kind of learned that if it's a negative, we go to the left. If it's positive, we go to the right. So that is still kind of holding true. Next thing we need to figure out is how many petals are there? If n is an odd number, then there are n number of petals. If n is an even number, then there are 2n number of petals. And if n is 1, then it's not a rose at all, but it's actually going to be a circle. To determine how many degrees are between each petal, we're going to do 360 degrees, because that's a full circle, divided by the number of petals. And then lastly, the final thing we need to know, we need to remember all the sine and cosine values of the quadrantals. Okay, so here, I'll just make it up here. Okay, so we remember we have ordered pairs of 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Sine is equal to y, cosine is equal to x. Okay, so sine of 0 degrees would be 0. Sine of 90 degrees would be 1. Sine of 180 is 0. Sine of 270 is negative 1. You guys might also recognize this pattern from when we graphed sine and cosine graphs. We always went for sine 0, 1, 0, negative 1. For cosine, we went 1, 0, negative 1, 0. And if we look, those are all the x values of those ordered pairs. So now let's actually get into a problem. I know I've told you a ton of info, and what we're going to see is that graphing is actually going to be pretty easy and straightforward. What's going to take a little bit of time is just figuring out what info do we need to know. So number 1 says r equals 5 cosine 2 theta. So the first thing that I want to highlight is that we have a 5 there. Okay, and we'll kind of talk about that in a second. Our other number I want to highlight is a 2. So n is 2. Since 2 is an even number, that means that we are going to have 4 petals. And the reason why we did 4 is because if n is even, I need to double that. So 2 times 2 is 4. Since this is a cosine graph, our first petal is going to be at 0 degrees. And our degrees between petals are going to be 360 divided by the number of petals, which would give us 90 degrees. Now, to determine how far out we're going to learn that it actually is going to be this A value. And the reason why that works, if I went ahead and substituted in R equals 5 cosine 2 times 0 degrees, cosine of 0 we learned is 1. So R equals 5 times 1, which is 5. So that tells me 0 degrees is an ordered pair. And what we're going to see is that this is always true. It's always going to be whatever our A value is. So how do we actually graph this? Okay, so I'm going to go ahead and go out 1, 2, 3, 4, 5 and not move at all. Then I'm going to move 90 degrees, 90 degrees, and 90 degrees again. Now, those are like the endpoints of all of our like petals. I couldn't think of the word there. It's a petal. So I'm going to go ahead now, and this is just a sketch, so I'm going to draw each petal. I know it goes between the origin and the point that I have gone ahead and plotted out. And this, my friends, is a rose. And honestly, it's that simple each time. So let's go ahead and look at this next one. Okay, this next one, we have R equals 6 sine 2 theta. So once again, I want to highlight this 2. That is our n value. So that means that we're going to have 4 petals because 2 is an even number. 2 times 2 is 4. Our first petal, since this is a sine graph, is going to be at 90 degrees divided by whatever our n value is, which is 2. So our first petal here is at 45 degrees. Degrees between petals, I'm doing 360 divided by the number of petals, and we get 90 degrees. So based on what we've seen, I'm thinking we're going to go out 6, but let's just double check and make sure that this works. So if I substitute in 45 degrees, okay, because that's where we said that our first petal is going to be, so that's why I'm using this here. In our previous one, we said our first petal was at 0, so we put 0 degrees here. So I get R equals 6 times the sine of 90 degrees. The sine of 90 degrees is 1, so I end up getting 645 degrees. So if we're graphing this, I'm going to go out 1, 2, 3, 4, 5, 6, and I'm going to go 45 degrees. Remember, each of these lines is worth 15. So 1, 2, 3, 4, 5, 6. I'm going to go up 3 lines, and then from here, I need to go 90 degrees. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Okay, now once again, I've already said this, but this is a sketch. But if we substituted in some of these other values, we would get ordered pairs that would form this rose. Okay, number 3, R equals -5 cosine 3 theta. Our n value is 3. This is the first time that we have had an odd number. When we have an odd number, that is just the number of petals. Since this is a cosine graph, our first petal is going to be at 0 degrees. This time, to find the degrees between petals, I'm doing 360 divided by 3, which is 120 degrees. And I'm thinking we're going to go out -5, but let's just make sure mathematically that that works. Okay, I get R equals -5 times the cosine of 0, which is 1, which is -5. And honestly, guys, once we get the hang of that, I don't need to write this out every time. I just want to show us mathematically that it works. I'm not just making something up for you guys. Some of you would care less, but it's okay. So negative 5, 0 means I'm going to the left 1, 2, 3, 4, 5 and putting a point. Now from here, I need to travel 120 degrees. And I just want to point out that it does not matter which direction we travel. It's going to work out just fine either way. I'm so used to going counterclockwise that that's how I'm going to move. So I'm going to go, let's see, 90, 120. Then I'm going to move the other way, 90, 120. So I'm going to go ahead and plot this rose, and there we go. So roses are that simple. We just need to understand and recognize that it is a rose. Just kidding, we have one more. Here we go. So this time our N value is 3, so we have 3 petals. Since it's sine, I'm going to do 90 divided by 3, so my first petal is at 30 degrees. Degrees between petals, 360 divided by 3 is 120 degrees. And I am just going to write out that my first point is at 530 degrees. So I'm going to go to the right, 1, 2, 3, 4, 5, and go up 30 degrees. Now from there, I need to move 120. So that would take me, let's see, 30, 60, 90, 120 right there. And then 30, 60, 90, 120 would be right there. So that makes all of our petals equidistant from one another. Okay, so that is our first type of graph, which is a rose. And if you really want to make it pretty, we can color them. We don't have any shading, so that's just for fun. It's not showing their solutions. But if you want to make your homework or walkthrough pretty and colorful, go for it. Moving on, now we're going to talk about circles and lines. And we actually have 3 different general equations for circles. Okay, our easiest is when the center is at the pole. Remember, the pole is like what we normally call the origin. Okay, for a polar graph, it's called the pole. So things like r equals a, that means I'm going out a, and it's going to be just a circle all the way around that particular value. A circle that lies on the y-axis, here we have sine, remember sine, y, same thing, okay? So this is going to be a circle that goes either up or down. Cosine, we know, is connected with x, so that's going to be a circle that either goes right or left. So let's actually do some and see what these look like. So number 1, r equals 5. This is an example of that first type of graph of a circle. I'm going to go out 1, 2, 3, 4, 5, and I'm just going to draw a circle all the way around that particular circle on the graph. Now my circle is not perfect, and that's fine, okay? This is the easiest type of circle. That's all we would need to do. Okay, our next one, r equals negative 3 sine theta. I want to point out before I do anything that we can remember that if we ever get stuck, we can always make an r theta chart like we did in the last lecture, and we can go ahead and figure out ordered pairs. Okay, but our shortcut, we know sine is y. This is telling me to go out negative 3 in the y direction. I know y is up and down, so I'm going to put a point at the pole, and I'm going to put a point down 3. And I'm going to draw a circle that connects those two. Now I want to point out that this looks really similar to a rose. Okay, and remember when we talked about the number of petals in a rose, we said if our n value is 1, it's actually a circle. And this is an example of that. Number 3, r equals 6 cosine theta. We know cosine is x. Since 6 here is positive, that means I'm going to go to the right 1, 2, 3, 4, 5, 6. And I'm also putting a point at the pole. For me, I have a tougher time drawing these circles just because with all the other circles going on, it looks weird, but that's what it would look like. Okay, so just a quick question. Where would the graph of r equals 3 sine theta be located? And this would be located up. This would be a top graph because we know sine is y and it's positive. Okay, so hopefully that gives us a good idea about what to do on circles. Let me erase the line I just drew. Okay. General equations for a line. We have 3 different types of lines. First is r sine theta equals a. And didn't we already learn that r sine theta is y? So this is just y equals a number. R cosine theta we learned is x equals, so that would be x equals a number. And then a line through an angle, we're just going to see theta equals an angle. And we actually saw some of these last lecture when we were trying to convert things from polar to rectangular and back and forth. So let's go ahead and go through these. R sine theta equals 4. So I'm just going to write y equals 4 just to remind me that that is a horizontal line. So I'm going to go up 1, 2, 3, 4. And I'm just going to draw a horizontal line. Okay, next, r cosine theta we know is x, so x equals -6. So that means I'm going to go to the left 1, 2, 3, 4, 5, 6. And I'm going to draw a vertical line going up and down. It's a little crooked, but that's okay. Lastly, theta equals 2 pi over 3. That means that this line is on this angle. If I forget what that angle is, remember that I can always convert it by multiplying it by 180 over pi, and I end up getting that this is 120 degrees. So if I'm graphing this, I know that 120 degrees would be over here. So I'm going to go ahead. Let me move up actually. And I'm just going to draw a line. There we go. That is on that particular angle. Now, I want to point out that it also covers the angle down here. So this could be called a few different things. It could be called 120. This is the same graph as if it was 300. Okay, so those are what circles and lines look like. In fact, here we go. It says, find another polar equation to represent the same line. Okay, we could write a few things. I could say that this is negative pi over 3. Because technically what we did move 60 degrees in a clockwise manner. Okay, I also said it was like 300 degrees, which would be like 5 pi over 3. It also could have been equal to negative 4 pi over 3, because that would take us back up to this angle right here. So once again, there's lots of ways that we can name angles in polar. So just a little glimpse of that for you guys. Moving on, our next type of polar graph is something that we call a limacon. It's a fun French word. So our general equations for limacons are right there. So we have r equals a plus b sine theta and r equals a plus b cosine theta. So what makes these very different are the fact that it is a binomial. Okay, for rows we saw that it was a monomial. Here we saw that these are binomials. So there are 3 different types of limacons, and it really depends on the values of a and b. So when we have the absolute value of a equals the absolute value of b, we call that a cardioid or a heart. Okay, we call it a cardioid, but we know the shape is like a heart. When the absolute value of a is greater than the absolute value of b, we call it dimpled, and it kind of looks like a bean. And when the absolute value of a is less than the absolute value of b, we call it an inner loop. So to graph, what we're going to do, first we need to determine what type of limacon it is, and then we're going to make an r theta chart and use all the quadrantal angles 0, 90, 180, and 270. Okay, so that is our plan. So looking at number 1, I noticed that the absolute value of 2 and the absolute value of 2 are equal to each other. So this is going to be a cardioid. So now I'm going to have to determine where are these ordered pairs going to be. So at 0 degrees, I'm going to have r equals 2 plus 2 times sine of 0 degrees. I know that the sine of 0 degrees is 0, so I get 2 plus 0, which is 2. Okay, next I have r equals 2 plus 2 sine of 90 degrees. Okay, for sine of 90 degrees, I know sine of 90 degrees is going to be 1. So I get 2 plus 2, which is 4. Next, we're going to do r equals 2 plus 2 sine of 180. Sine of 180 is also 0, so I get 2 plus 0, which is 2. And then lastly, r equals 2 plus 2 sine 270. Sine of 270 is negative 1, so 2 times negative 1 is negative 2, plus 2 gives us 0. So what this did was give us 4 different ordered pairs that we're going to now go ahead and plot on this graph here. So I'm going to plot 2, 0, 4, 90 degrees, 2, 180, and then 0, 270. Since we said this is a cardioid, that means that it is going to look like a heart. Now, I want to point out a cardioid is always going to have a point that is at the pole. And the question I have for you guys, where do you notice equal r values? And we can see that on the x-axis here, we do have some equal values. So 2 and we have negative 2. And we'll see for cosine, we see some stuff like that as well. Now, the reason why it's like this, we know sine goes with y, so it is symmetric on the y-axis. If I fold it on the y-axis, it would line up. If it's cosine, we're going to see that it is symmetric on the x-axis. Okay, so our next one, r equals 3 minus cosine theta. So I'm going to compare 3 and negative 1. And the absolute value of 3 is greater than the absolute value of negative 1, so this means that it is dimpled. And what we're going to see is that a dimpled looks very similar to a cardioid. The only difference, we're not going to have a point at the pole. So I'm going to do r equals 3 minus cosine of 0 degrees. I know cosine of 0 is 1, so 3 minus 1 is 2. R equals 3 minus cosine of 90. Cosine of 90 is 0, so I get 3. R equals 3 minus cosine of 180. Cosine of 180 is negative 1, so 3 minus negative 1 is 4. And then lastly, 3 minus cosine of 270 is 0, so I get 3. So if I'm plotting this, I have points at 2, 0, 3, 90, 4, 180, and 3, 270. So it's going to look something like this. Now notice this looks really similar to a cardioid, but once again, a cardioid has a point that is at the pole. And equal r values this time, since it was a cosine, it's symmetric on it is symmetric on the x-axis. If I fold it on the x-axis, it would be a mirror image. So we notice that these values are the same. Okay, number 3, once again, I can tell that this is a limacon because we have this addition here. And I'm going to go ahead and compare the absolute value of 2 and 4. And this time, the absolute value of negative 2 is less than the absolute value of 4. So this means that this is an inner loop. Okay, and we're going to see what that looks like when we graph it. So I'm going to start r equals negative 2 plus 4 times sine of 0. Sine of 0 is 0, so I get negative 2. r equals negative 2 plus 4 sine of 90 degrees. I know sine of 90 is 1. Negative 2 plus 4 is 2. r equals negative 2 plus 4 times the sine of 180. Sine of 180 is 0, so I get negative 2. And then lastly, r equals negative 2 plus 4 times the sine of 270. I know that the sine of 270 is negative 1, so I get negative 2 plus negative 4, which is negative 6. Now when we're graphing a lot of these ordered pairs, notice we have negative values, so that means that I need to go in the opposite direction. So I have negative 2, 0. Then we have 2, 90 degrees. Negative 2, 180. And negative 6, 270. So what we're going to notice when we have an inner loop is that we will have 2 points that are on the same axis. So we'll have 2 points that are on the positive x-axis or the positive y-axis or negative x-axis, negative y-axis. And the way that this is going to be graphed is that we have this loop, okay, that kind of connects these points together. So those are 3 different graphs. We're not going to do a ton of these because it's pretty repetitive. It's just practice knowing how to identify it and then figuring out what those ordered pairs should actually look like. Now, the final thing we're going to talk about are what we call lemniscates. Lemniscates, okay, we have 2 different general equations, and the way that I can always notice this is the r squared. Okay, we have r squared equals a squared sine 2 theta, and this is always going to be 2 theta. A squared is going to be the only constant. And the way that we graph it, if it is a sine graph, it's either going to be at 45 degrees or negative 45 degrees. And it depends if the equation is positive, it's going to be at 45. If it's negative, it's at negative 45. If it is cosine, it's either going to be horizontal or vertical. If it is horizontal, that means that this is positive. If it is vertical, it's because that is negative. And what we're going to see is these kind of look like bow ties. Okay, so the way that we're going to graph this, number 1 says r squared equals 16 sine 2 theta. I see this r squared, and that really shows me right away, okay, this is different than anything we've done. So I'm going to really look at this 16, and I'm going to figure out, okay, what is plus or minus the square root of 16? So it would be plus or minus 4. So since sine is positive, that means that I'm going to go 45 degrees and negative 45 degrees. So I'm going to go to the right 1, 2, 3, 4 and put my point, and then go out 1, 2, 3, 4 and put my point. I don't think I went far enough there. Let's see, 1, 2, 3, 4, 1, 2, 3. There we go. And then this graph is just going to look like a bow tie. It kind of looks like a rose that has 2 petals, but as you guys may know, it's impossible for a rose to have 2 petals because if n was 2, there would be 4 petals, and if n was 1, it would actually be a circle. So let's look at number 2 here. It says graph r squared equals 9 cosine 2 theta. So this time we have 9. So I'm going to figure out what is the plus or minus the square root of 9, and it is 3. Since cosine is positive, that means I'm going to be at 3, 0 degrees, and negative 3, 0 degrees. So I'm going to go to the right 1, 2, 3, and I'm going to go to the left 1, 2, 3, and go ahead and draw my bow tie. That looks super ugly, but hopefully you guys get the hang of it. So my question for you guys then is, where would r squared equals negative 16 sine 2 theta be located? Okay, and we can see it's sine, and since this is negative, that means that it's going to be at negative 45 degrees, which really means it would be in quadrant 2 and quadrant 4. If we have negative 9 cosine 2 theta, this time, since it's cosine, we know it's going to be on an axis, but since it's negative, I know that it is going to be at 90 degrees. Or we could think of that as it's going to be vertical. Okay, so this was a quick overview of each of those particular graphs separately. The next video that I'm going to make is going to just be going through a bunch of problems where we're going to have to analyze what type of graph it is and then go ahead and figure it out.